Space itself can stretch and squeeze. For over a century, we believed these ripples in spacetime were real, a prediction from Einstein's mind that felt almost untouchable. Now, we are not just believing, we are listening. Gravitational waves are a new sense for the cosmos, and the discoveries they have delivered are rewriting our cosmic textbooks. By the end of this journey, you will understand 30 revelations that have fundamentally reshaped modern astronomy. We will uncover how colliding black holes revealed a population of monsters we never knew existed, and how a single cosmic crash solved the ancient mystery of where gold comes from. What do you think it means to finally hear the universe speak? It began with a whisper in the data, a faint cosmic tremor that arrived on Earth on September 14, 2015. After a century of waiting, the Laser Interferometer Gravitational Wave Observatory, or LIGO, had finally heard it. The signal was officially named GW150914, but its sound would become legendary. It was the final death spiral of two black holes, each one a monster roughly 30 times heavier than our Sun, locked in a final dance over a billion light-years away. Their collision converted an amount of mass equivalent to 3 whole suns directly into pure energy, rippling outward as gravitational waves. For the final few milliseconds before they merged, the system shone with more power than all the stars in the observable universe combined. And we heard it all. The signal itself was a simple rising tone, a chirp that started at a low frequency and swept upwards in both pitch and intensity before ending abruptly. That chirp was the sound of spacetime itself ringing like a bell. This single event confirmed a cornerstone prediction from Einstein's theory of general relativity, proving that these ripples in the fabric of the cosmos were not just mathematical curiosities. It was the culmination of decades of painstaking work, a triumph of engineering and human curiosity that flung open a brand new window on the universe. We were no longer just stargazers. We had become listeners. That first chirp could have been a cosmic anomaly, a singular event in an otherwise silent universe. But then came another and another. Within just the first 2 observing runs, the LIGO and Virgo collaborations had cataloged over a dozen confident detections of binary black hole mergers. The message was stunningly clear. The collision that produced GW150914 was not a rare fluke. It was a routine occurrence in our dynamic and often violent cosmos. We had discovered that binary black hole systems are common, and their final, furious mergers are a frequent source of the gravitational waves that constantly wash over our planet. This confirmation opened our ears to a chorus we never knew was there, revealing an entire population of stellar mass black holes that had been completely hidden from our telescopes. These are not the supermassive giants at the centers of galaxies. These are the end states of the most massive stars, and their detected masses have been a profound surprise. We are finding black holes weighing in at 30, 40, even 50 times the mass of our Sun. These sizes challenge our very models of how massive stars live and die. Conventional astrophysics suggested that the violent death throes of such large stars, in events known as pair instability supernova, should tear them apart completely, leaving nothing behind. They were not supposed to leave black holes of this size, yet the data from gravitational waves tells us they do, and often. The statistics are staggering. Based on the rate of detections, astronomers now estimate that a binary black hole merger happens somewhere in the universe roughly every few minutes. Every few minutes, A pair of these dark ghosts ends its billion-year dance in a fraction of a second that briefly outshines the entire universe. Each event is a fossil record, telling us a story about the life and death of the two massive stars that created these black holes long ago. They speak of binary systems born together, evolving together, and ultimately collapsing into darkness, only to be found by us through the faintest ripples in spacetime. What other secrets about the lives of stars are these dark messengers carrying? But the universe had an even bigger surprise in store, one that would unite two completely different ways of seeing the cosmos. On August 17, 2017, the LIGO and Virgo detectors felt a new kind of ripple. This signal was different from the sharp chirp of black holes. It was a longer, richer tone, lasting for nearly 100 seconds. This was the sound of two neutron stars, the incredibly dense corpses of massive stars, spiraling together in a distant galaxy. The moment the alert went out, a global race began. For the first time ever, we had a gravitational wave signal that was precise enough to point telescopes in the right direction. The entire astronomical community sprang into action. Within hours, dozens of telescopes on the ground and in space swiveled to the same patch of sky. And they saw it, a brand new point of light, glowing fiercely in the galaxy NGC 4993. This was the kilonova, the brilliant radioactive fireball created by the violent merger. We were no longer just listening to the universe. We were watching the same event unfold in gravitational waves and in light. This was the dawn of multi-messenger astronomy, and it answered one of the oldest questions in science. Where does the gold in your jewelry, the platinum in a catalytic converter, actually come from? The spectra from that kilonova revealed the unmistakable fingerprints of newly forged heavy elements. In the extreme conditions of that collision, neutrons were rapidly captured by atomic nuclei, creating a cosmic alchemy that produced staggering amounts of gold, platinum, and other precious metals. In that single event, scientists estimate that an amount of gold many times the mass of our entire planet was forged and blasted out into space. A single cosmic crash solved a mystery that had puzzled us for generations. The very elements that make up our world and enable our technology were born in the most violent explosions imaginable. We are, all of us, made from the ashes of distant stars. That single event did more than just create the gold in a wedding ring. It fundamentally changed how we explore the universe. Before August 17, 2017, we were effectively deaf to the cosmos. We could see the light from stars and galaxies, but we were missing the soundtrack. The detection of both gravitational waves and light from the same neutron-star collision marked the true birth of multi-messenger astronomy. It was the moment we gained both sight and sound. Think of it like watching a silent movie your entire life, and then suddenly hearing the characters speak, the music swell, and the sound effects roar. Your understanding of the story becomes infinitely deeper and more complete. For the first time, we had a full sensory experience of a cosmic cataclysm. The gravitational waves told us the precise masses of the colliding objects and the dynamics of their final, furious dance. The light from the kilonova showed us the aftermath, the brilliant radioactive debris, and the specific elements being forged within it. This was not just two separate observations. It was a single story told in two different languages, and for the first time, we were fluent in both. This incredible breakthrough was made possible by an unprecedented level of global cooperation. The moment the LIGO and Virgo detectors identified the signal, an automated alert was sent to observatories across the globe. A coordinated race against time began, as telescopes on every continent and in space scrambled to find the fading ember of light. This was not a competition. It was a collaboration with data shared openly and instantly across international borders. Astronomers in Chile, Hawaii, and in orbit around Earth all worked in concert, piecing together the event like detectives at a cosmic crime scene. This new way of working, where a vibration in spacetime triggers a global observing campaign, is now a cornerstone of modern astronomy. It is revolutionizing our ability to study the most violent and energetic events in the universe. We are no longer passive observers of a silent sky. We are active listeners, ready to turn and look the moment the universe speaks. And what other conversations might we be able to hear and see next? The cosmic menagerie of black holes suddenly gained a new mysterious member. For decades, we had only known of two kinds. There were the stellar mass black holes, the ghosts of dead stars, and the supermassive behemoths that anchor entire galaxies. A vast gap existed between them, a chasm spanning from a few dozen to millions of solar masses. What existed in that immense void was one of astronomy's great mysteries. Then, in May of 2019, the LIGO and Virgo detectors recorded a signal that was utterly unlike anything before. It was not the quick, high-pitched chirp of two small black holes. This was a low, heavy thud, a brief burst of vibration named JW190521. It was the sound of an immense collision. Two colossal black holes, one weighing 85 times the mass of our Sun and the other 66 times, spun around each other and merged. The resulting single object was a black hole of about 142 solar masses. This number is profoundly significant. It sits squarely in the territory of the intermediate mass black hole, a class of object that had been theorized but was incredibly difficult to confirm. This was the missing link, caught in the act of its own creation. The heavier of the two parent black holes was itself a puzzle. At 85 solar masses, it falls squarely into a forbidden range known as the pair instability gap. According to stellar physics, a star that dies with a core mass between about 65 and 135 solar masses should not form a black hole at all. It should be completely obliterated in a cataclysmic supernova that leaves nothing behind. Yet, the gravitational waves tell us this object existed. Its very presence challenges our fundamental understanding of how massive stars die, suggesting they might collapse directly into black holes through a different, unseen process. Or perhaps this black hole was itself the product of an earlier merger, a second-generation monster. The discovery of this intermediate mass black hole opens up a thrilling new line of inquiry. How do these objects form? Are they the ancient seeds from which supermassive black holes grow, accumulating mass over billions of years? Or are they built through a hierarchical chain of mergers in dense stellar environments, with black holes constantly colliding to create ever larger ones? The detection of JW190521 suggests that the universe is busy building bigger and bigger black holes, and we are now privy to the construction process. We are witnessing the potential birth of a future galactic giant. This discovery of an 85 solar mass black hole struck at the very foundation of stellar astrophysics. It forced us to confront a profound gap in our knowledge, a forbidden zone predicted by our theories of how stars die. This is the pair instability supernova gap. To understand why this is so revolutionary, we need to look at the final, violent breaths of a truly massive star. When a star with a core mass between roughly 65 and 135 times that of our Sun reaches the end of its life, the intense heat in its core begins to spontaneously create matter and antimatter pairs, specifically electron and positron pairs. This process is a cosmic catastrophe. It robs the core of the radiation pressure that was holding the star up against its own immense gravity. The star loses its internal support, and a runaway thermonuclear explosion ensues. This pair instability supernova is so utterly violent, so complete, that it does not leave behind a black hole or a neutron star. It completely obliterates the stellar core, scattering all of its material into the void. Nothing remains. According to every textbook, a black hole with a mass of 85 suns should not exist. It should have been erased from the universe by its own death throes. Yet, the gravitational wave signal GW190521 tells us it was very real. So how did it get there? How did this cosmic rule breaker form? One compelling possibility is that this forbidden black hole was not born from a single dying star. It might be a second-generation object, the product of an earlier merger between two smaller black holes in a dense star cluster. In this scenario, two black holes of perhaps 40 solar masses each, which are themselves permissible under stellar theory, could have found each other, spiraled together, and merged to create the 85 solar mass anomaly we detected. This hierarchical merging presents a universe that is far more dynamic and interconnected than we ever imagined. Black holes are not just solitary endpoints. They can be building blocks, colliding and combining over cosmic time to create ever larger monsters that defy our expectations for single stars. This forces a complete re-examination of the final moments of the most massive stars. Perhaps some stars in this forbidden mass range can still collapse directly into black holes through a different, more subdued process that avoids the pair instability entirely. Or maybe our understanding of the physics inside these dying giants is still incomplete. The very existence of these gap black holes tells us that the universe is more inventive than our models, always ready to reveal a new path, a new method of creation we had not considered. What other cosmic laws are we on the verge of rewriting with the next ripple through spacetime? This new way of listening to the cosmos is even letting us measure the universe itself in a way light never could. Gravitational waves provide a completely independent method to measure the Hubble Constant, the rate at which our universe is expanding. For decades, astronomers have relied on light to calculate this fundamental number, using the brightness of distant supernova or the faint glow of the early universe. But these different methods have begun to produce a troubling inconsistency. They do not agree, creating a major puzzle in modern cosmology. The arrival of gravitational waves offers a way out of this impasse. The technique uses a binary neutron-star merger as what scientists call a standard siren. When we detect the gravitational waves from such a collision, the signal itself encodes crucial information. The shape and strength of the waves tell us the intrinsic loudness of the event, which in turn reveals its true distance from Earth, all without a single candle or mile marker. It is a direct cosmic ruler. Then, by quickly pinpointing the host galaxy with optical telescopes, we learn how much the light from that galaxy has been stretched, or red-shifted, by the expansion of the universe. By combining the direct distance from the gravitational waves with the red shift from the light, we can calculate the Hubble constant directly, completely independent of the cosmic distance ladder. This is a revolutionary check on our previous work. The first such measurement from the neutron-star merger in 2017 already began to weigh in on the cosmic tension. Its value intriguingly fell between the two competing numbers from traditional methods, not definitively solving the puzzle, but proving this new tool works. As we detect more of these standard sirens, we will build a more precise measurement, potentially revealing which of our old methods contains a hidden flaw, or if we need entirely new physics to understand why the universe is expanding at the rate it is. We are no longer just measuring the cosmos. We are cross-examining it with a new and powerful witness. The final collision of two black holes is not the end of the story. In the immediate aftermath of the merger, the newly formed single black hole does something remarkable. It rings, like a bell struck by a mighty hammer. It vibrates, its very surface oscillating in a complex set of tones before settling into a perfect, silent sphere. These vibrations are not sound waves in the traditional sense. They are oscillations of the event horizon itself, the point of no return, and they imprint themselves directly onto the gravitational waves that ripple outward. This phase is known as the ringdown, and it is a treasure trove of information. By carefully analyzing the frequency and decay rate of these dying vibrations, scientists can weigh the final black hole and measure how fast it is spinning. But the ringdown does much more than that. It provides one of the most direct tests ever conceived for Einstein's theory of general relativity in the most extreme gravitational environment possible. According to the theory's predictions, a black hole is an object of stunning simplicity. The famous no-hair theorem suggests that a black hole can be completely described by just three properties: its mass, its electric charge, which is typically negligible, and its spin. All other information about the matter that formed it, or that it has consumed, is lost forever behind the event horizon. It has no hair, no distinguishing features beyond those three numbers. The ringdown is the fingerprint of this perfect simplicity. The specific tones we detect in the gravitational wave signal should match exactly what general relativity predicts for a black hole of that specific mass and spin. If the tones were different, if we heard overtones or frequencies that should not be there, it would be a sign that something is profoundly wrong with our understanding. It could mean that the object created in the merger is not a true black hole as described by Einstein, but something even stranger, perhaps a naked singularity or an exotic stellar remnant that lacks an event horizon. So far, the ringdown from every detected merger has sung in perfect harmony with Einstein's predictions. Each clean, simple tone is a powerful confirmation that we are indeed observing the genuine article, a true black hole born from chaos, its complex past erased, now defined by nothing but its mass and its spin. We are listening to the purest objects in the universe find their new, silent form. The sheer number of these cosmic crashes has been a profound shock. Our detectors have been listening for only a few years, and already the catalog of black hole and neutron star mergers numbers in the dozens. The observed rate is far higher than most theoretical models ever predicted. The universe, it seems, is a much more violent and dynamic place than we ever gave it credit for. This unexpectedly high merger rate forces us to reimagine the entire life cycle of binary systems. How do two massive stars, born together, manage to stay bound through their turbulent lives and violent deaths, only to end up close enough to merge billions of years later? The process must be far more common and efficient than our simulations suggested. It tells us that the pathways to creating these tight, deadly pairs are not rare cosmic flukes, but rather a standard feature of stellar evolution in many galaxies. This has monumental implications for our models of galactic evolution and cosmic history. If black hole and neutron star mergers are this frequent, they are injecting tremendous amounts of energy and heavy elements into interstellar space at a staggering pace, potentially reshaping the formation of new stars and planets. The very building blocks for rocky worlds like Earth, the gold and platinum forged in neutron star collisions, are being produced and scattered throughout the cosmos at a rate that could make life-supporting planets more common than we dream. We are hearing the background hum of a universe constantly rebuilding itself, one cataclysmic collision at a time. That violent collision of neutron stars did more than just create gold. It gave us our first direct look into the heart of one of these incredible objects. When two neutron stars spiral inward, they do not simply fall toward each other like two featureless points. Their immense gravitational fields act upon each other in a cosmic tug-of-war, stretching and squeezing them long before they ever touch. This stretching is called tidal deformability. Picture the ocean tides on Earth, raised by the moon's gentle pull. Now imagine that pull is a billion times stronger, exerted by an object just as dense, distorting a sphere of nuclear matter 10 miles across. This violent stretching leaves a distinct, subtle imprint on the gravitational wave signal, a kind of signature in the final moments of the spiral. For the first time, with the event in 2017, we were able to read that signature clearly. It told us that these particular neutron stars were relatively soft, meaning they were more deformable than some of the most extreme theories had predicted. This single measurement immediately ruled out a host of theoretical models for what happens inside a neutron star. Some physicists had hypothesized that the core of a neutron star might contain exotic states of matter, like a soup of free quarks, or might transform into a hyperon star, a form of matter so strange it would be incredibly stiff and resistant to deformation. The data from the gravitational waves told us that if such states exist, they cannot make the star impossibly rigid. This tidal deformability measurement is a direct probe of the neutron star equation of state. This equation is perhaps the most sought-after piece of information in all of nuclear physics. It is simply the relationship between the pressure inside the star and its density, and it dictates everything about the star, from its maximum possible size to how squishy or hard it is. For decades, we have had to infer this equation from laboratory experiments and theoretical guesses. Now, gravitational waves provide a remote laboratory, one with conditions of density and pressure we could never hope to recreate on Earth. By measuring how much a neutron star stretches before it shatters, we are learning the fundamental rules that govern matter itself under the most extreme pressures in the universe. Each new neutron star merger we detect adds another data point, another piece to this grand puzzle, slowly revealing the true nature of the cosmic matter from which these incredible objects are made. The ultimate cosmic race was happening right in front of us, and for the first time, we had a front row seat. When the gravitational waves from that neutron star merger arrived on Earth, they were followed just 1.7 seconds later by a flash of gamma rays. This brief delay was not a coincidence. It was a critical test of one of Einstein's most fundamental predictions, that gravity and light travel at the exact same speed. According to his theory of general relativity, the fabric of spacetime itself is the medium for gravitational waves, and they should propagate at the speed of light, no faster and no slower. But what if Einstein was wrong? Many alternative theories of gravity, developed over the decades, predicted tiny deviations. Some suggested that gravity might travel infinitesimally faster than light, or perhaps a bit slower. The nearly simultaneous arrival of the gravitational and electromagnetic signals from the same event allowed scientists to perform a measurement of breathtaking precision. By comparing the travel times of the two signals across a journey of 130 million light-years, researchers concluded that the speeds of gravity and light are the same to within 1 part in 1 quadrillion. To put that almost unimaginable precision into perspective, it is like timing 2 race cars and finding they crossed a finish line separated by a distance less than the width of a single atom. This incredible result slammed the door on a vast range of alternative theories of gravity. Any theory that predicted a significantly different speed for gravity was instantly and definitively ruled out. It was a stunning, direct validation of a key pillar of general relativity, proving that Einstein's vision of a unified spacetime, where light and gravity march in perfect lockstep, holds true even across cosmic distances. The universe itself was the laboratory, and the result was a resounding confirmation of a century-old idea. Even the most rigid cosmic classifications can suddenly blur. The universe has presented us with a new kind of puzzle, an object that defies our neat categories. For decades, astronomers operated with a seemingly clear rule. Neutron stars, the ultra-dense remnants of collapsed stars, were thought to have a maximum mass of around 2.2 times that of our Sun. Any heavier, and the force of gravity would be too overwhelming, crushing the star into a black hole. The lightest known black holes, in turn, started at around 5 solar masses. This left a clear gap between 2.2 and 5 solar masses, a silent desert where no compact objects were supposed to exist. Then came the signal known as GW190814. Detected in August of 2019, it was the collision of a 23 solar mass black hole with a much smaller companion. The mystery was the smaller object. It weighed 2.6 solar masses. This mass sits squarely in the middle of that forbidden gap. So, what exactly did the black hole consume? We are faced with a fundamental identity crisis. Is this the most massive neutron star ever discovered? A cosmic champion that somehow resisted collapse against all odds? Or is it the lightest black hole ever found? A tiny, featherweight singularity that challenges our ideas of how black holes are born. Each possibility unravels a different thread of our understanding. If it is a neutron star, then our models of the nuclear forces that hold these objects up against gravity are critically wrong. The equation of state, the very rulebook for matter at these densities, would have to be rewritten to allow for a star so massive and robust. It would mean neutron stars can be far more resilient than we ever dreamed, potentially changing our estimates of how many of them exist in the cosmos. If, however, this 2.6 solar mass object is a black hole, it creates a different set of problems. How does a star collapse to form such a lightweight black hole? Standard stellar evolution models do not easily produce black holes in this mass range. It suggests there might be a new, unknown pathway for the death of stars, one that creates these diminutive dark objects. This single gravitational wave detection has turned a theoretical gap into a real, observed territory. It is no longer an empty desert, but a landscape where new physics might be hiding. The very boundaries between a neutron star and a black hole, once thought to be clear and distinct, are now revealed to be a fascinating and mysterious frontier. What other ambiguous objects are waiting in the shadows, ready to challenge what we think we know? Even the path of a ripple in spacetime is not perfectly straight. As gravitational waves journey across the cosmos for billions of years, they do not travel through empty space. They pass through the gravitational fields of every galaxy, every cluster of dark matter, every massive object in their path. And according to a prediction made decades ago by physicists Lev Landau and Evgeny Lifshitz, these background fields should subtly distort the waves, causing a faint scattering or blurring of the signal by the time it reaches us. For a long time, this was considered an almost undetectable theoretical curiosity. Now, with the sheer number of signals in our catalog, advanced data analysis is beginning to find the first tantalizing hints of this Landau-Lifshitz blur. The effect is incredibly subtle, like trying to detect the faintest of echoes in a vast hall. Scientists are not looking at one single wave, but rather comparing the collective properties of many different detections, searching for a consistent, tiny distortion that betrays the gravity-filled medium the waves have traveled through. This is not just a minor detail. Confirming this blur would be a spectacular test of gravity's nonlinear nature. What does that mean? In Einstein's theory, gravity is not a simple, one-way force. It begets more gravity. The energy contained in a passing gravitational wave itself creates a tiny gravitational field. This means the wave is not just a passenger moving through the cosmos. It is an active participant, its own path slightly bent and scrambled by the collective gravity of the universe it is trying to traverse. It is gravity itself feeling gravity. Proving this would show that the fabric of spacetime is an interactive, dynamic medium, where even its own ripples are subject to its rules. A beautiful and profound circularity that lies at the very heart of general relativity. We are on the verge of seeing the universe not just as a container for events, but as a complex, interacting substance that leaves its fingerprint on every message it carries. Beyond the distinct chirps of individual collisions lies a far grander symphony. This is the stochastic gravitational wave background, a faint, constant hum created by the combined roar of every binary black hole merger that has ever occurred throughout cosmic history. It is the residual vibration of the universe. A sea of spacetime ripples so numerous and overlapping that they blend into an indistinguishable, all-pervasive noise. Think of it like standing in a crowded stadium. You can pick out the shouts of a few nearby individuals, but beneath it all is the steady roar of the entire crowd, a collective sound that has no single source. This gravitational hum is the same, the accumulated whisper of billions upon billions of cosmic crashes, all echoing together across time and space. Detecting this background noise requires a completely different kind of instrument, one far larger than any laser interferometer on Earth. Scientists are using the galaxy itself as their observatory, with pulsars as their precision tools. Pulsars are the rapidly spinning cores of dead stars, acting as cosmic lighthouses that beam radio waves toward Earth with a regularity that rivals the most accurate atomic clocks. By monitoring an array of these pulsars scattered across our galaxy for over a decade, researchers are listening for a specific, coordinated disturbance. As the faint hum of the gravitational wave background washes through the galaxy, it minutely stretches and squeezes the space between these pulsars and Earth. This causes the otherwise perfectly timed pulses to arrive just a little early or a little late, in a correlated pattern across the entire sky. It is an attempt to detect a change in timing smaller than 1/1,000,000th of a second, a feat of patience and precision that is now on the verge of paying off. The first tantalizing hints of this background hum are emerging from the data. Detecting it with certainty would open a completely new window into the cosmos. This hum would act as a census of the universe's population of supermassive black hole binaries, the colossal pairs that lurk at the hearts of merging galaxies. Their slow, stately dance, lasting millions of years, is a dominant source of this low-frequency rumble. By tuning into this frequency, we could learn how common these pairs are and how they eventually spiral together to form even larger giants. But the implications go even deeper. This primordial hum could also contain traces of even more exotic phenomena from the universe's earliest moments. It might carry the faint memory of cosmic strings, hypothetical defects in the fabric of spacetime left over from the Big Bang, vibrating like incredibly long, ultra-thin violin strings. Or it could preserve the vibrations from the period of cosmic inflation, the explosive expansion that occurred a fraction of a second after the universe began. We are listening for the echo of creation itself, hidden within the faintest static the universe has to offer. Even the silence of our detectors carries a profound message. We have not yet captured the unambiguous gravitational wave signal from a core collapse supernova, the final death scream of a massive star. But this absence of a signal is not an empty void. It is a powerful constraint, a whisper telling us what the universe is not doing. Every time a supernova explodes in a distant galaxy and our gravitational wave observatories hear nothing, we learn something critical. We learn that the explosion must have been remarkably symmetric. Gravitational waves are only produced by violent, asymmetric motions. If a star were to collapse and explode in a perfectly spherical manner, like an inflating balloon, it would produce no ripples in spacetime at all. The fact that we have not detected waves from these events tells us that most core collapse supernovae are far more spherical than some of the most dramatic theories had predicted. This non-detection is steadily ruling out models where the explosion is driven by powerful jets, or where the core fragments into lopsided clumps, which would create a strong, detectable gravitational wave signature. Instead, the silence is pointing us toward mechanisms where neutrinos, those ghostly subatomic particles, play the dominant role in gently pushing the stellar envelope outward in a more balanced, spherical fashion. This quiet data is a crucial piece of the supernova puzzle, helping us narrow down the exact sequence of events that tears a giant star apart. But the real revolution will come when a star in our own galactic neighborhood, perhaps Betelgeuse, finally reaches its end. The distance to such an event would be 1,000 times closer than any supernova we have observed in the gravitational wave era. The signal would not be a faint whisper lost in the noise. It would be a roar. For the first time, we would have a direct view into the very engine of the explosion, the chaotic dance of the collapsing core in the few tenths of a second before the shock wave breaks through the stellar surface. The gravitational waves would reveal the precise movements of the ultra-dense matter as it rebounds and forms a proto-neutron star, telling us if it wobbles wildly or spins up to incredible speeds. We would witness the birth of a neutron star or a black hole in real time, reading the story of its creation from the vibrations of spacetime itself. That single, nearby signal would answer questions we have been asking for a century, finally showing us the true heart of a stellar giant's death. Einstein's theory now faces its most demanding judges in the violent hearts of merging black holes. This is the regime of strong field gravity, a place where space-time is not merely curved, but whipped into a frenzy, conditions far beyond anything our solar system could ever provide. Here, general relativity makes very specific predictions about the nature of the gravitational waves produced. Scientists are performing exquisitely precise checks, looking for any tiny crack in the theoretical foundation. One critical test involves searching for dispersion. In many areas of physics, waves of different frequencies travel at different speeds. Think of how a prism separates white light into a rainbow of colors. But according to Einstein, gravitational waves should not do this. In the pure fabric of spacetime, a low-frequency rumble from a massive black hole and a high-frequency chirp from a smaller one must race across the cosmos at exactly the same speed. Any detected difference, no matter how minute, would signal a breakdown of general relativity in these extreme environments. So far, every observation confirms that gravity is gloriously dispersion-free. The waves all move in perfect lockstep. Another profound test looks at the very way these waves wiggle spacetime. General relativity predicts that gravitational waves have only two possible polarization states, often called plus and cross. They stretch and compress space in a very specific cross-shaped pattern as they pass. Yet, many alternative theories of gravity, devised to solve other cosmic mysteries, predict the existence of additional polarization states. Some theories suggest a scalar mode that would make space breathe, expanding and contracting in all directions at once. Others predict vector modes that would twist space like a corkscrew. Our sensitive detectors are now capable of searching for these ghostly extra patterns within the signals. To date, they have found nothing. Only the two classic polarizations predicted by Einstein over a century ago are present in the data. With every new black hole merger we record, the constraints on these alternative theories grow exponentially tighter. We are not just confirming Einstein was right. We are proving with ever greater certainty that his theory of gravity is the one that truly governs the most extreme interactions in our universe. The silent, colliding darkness is speaking with a clarity that is slowly silencing the competition. These dense cosmic cities offer a completely different path to collision. Far from the isolated emptiness of the galactic suburbs, globular clusters are ancient, spherical swarms of stars, packed together so tightly that a million suns could reside within a space just a few dozen light years across. In such a crowded neighborhood, stellar close encounters are not rare events. They are a fundamental part of life. It is in this chaotic environment that black holes, the heaviest residents, naturally sink to the center through a process called mass segregation. Imagine a crowd of people in a room where the heaviest individuals gradually settle to the middle. In a globular cluster, black holes do the same, creating a dense core of dark objects constantly interacting, a gravitational dance floor where partners are frequently swapped. Through a complex series of gravitational tugs, two single black holes can become gravitationally bound, forming a binary pair that had no shared stellar history. They were not born together. They found each other in the chaos. This dynamic formation channel stands in stark contrast to the isolated binary evolution we once thought was the primary source. That model required two massive stars to be born as a pair, evolve together, and survive two supernova explosions without having their orbit disrupted. The high merger rate we observe suggests the universe needs a more efficient factory, and these dense clusters are it. They provide a ready-made environment where black holes can rapidly find partners and, through further encounters, have their orbits tightened until they are close enough to merge within the age of the universe. This discovery forges a direct link between the gravitational waves we detect and the grand, dynamical evolution of entire star systems. The chirps we hear are not just the end of two stars. They are the echoes of a crowded cosmic ballroom, a testament to the relentless gravitational interactions that shape the lives of stars and the dark remnants they leave behind. The cosmic dance is not always a meeting of equals. While many of the black hole pairs we detect are well matched in size, the universe occasionally choreographs a far more lopsided performance. A signal named JW190412 revealed a system with a starkly asymmetric mass ratio. One black hole was roughly 30 solar masses, a familiar heavyweight. Its partner, however, was a lightweight champion at just 8 solar masses. This was not a duel between two giants. It was a cosmic waltz between a giant and a dwarf, and the resulting gravitational waves sang a much more complex song. When two black holes of equal mass spiral together, their gravitational wave signal is a relatively simple, clean chirp, but introduce a significant size difference, and the dynamics change completely. The smaller object spends its final moments whipping around the heavier one in a series of tight, fast orbits, tracing a complex path rather than a simple mutual spiral. This intricate motion imprints itself onto the gravitational waves, generating rich overtones known as higher harmonics. It is the difference between hearing a single, pure note from a tuning fork and the complex chord of a grand piano. These higher harmonics are not just a flourish. They are a new source of information, a key that unlocks details previously hidden from us. For the first time, we could clearly measure the precession of the smaller black hole's orbit. This means its entire orbital path was wobbling like a spinning top, a direct result of the immense frame dragging caused by the spin of the larger black hole. The signal from JW190412 revealed that the heavier black hole was spinning rapidly, a crucial piece of its history we could never have deduced from an equal mass merger. These lopsided systems offer a fresh and demanding test for general relativity. The complex waveform, with its multiple harmonics and precessional wobbles, must still perfectly obey Einstein's equations. Any deviation between the observed signal and the theoretical prediction would stand out like a sour note in a symphony, pointing toward new physics. By listening to these unbalanced duets, we are probing gravity in a new regime, learning not just that black holes merge, but precisely how they move in their final, frantic moments together. Our universe might be far roomier than it appears. For centuries, we have pictured reality as having 3 spatial dimensions, a stage with length, width, and height. But some of the most ambitious theories in physics, those seeking to unite gravity with the quantum world, propose a hidden architecture. They suggest the existence of additional, curled-up spatial dimensions, dimensions too tiny for our eyes or instruments to perceive directly. If they exist, these extra dimensions would offer gravity a new place to go. Just as sound seems to fade in a vast, open hall, gravitational waves could subtly leak into these hidden realms as they travel across the cosmos. Over immense distances, this leakage would cause the waves to arrive at our detectors slightly weaker than our standard models predict. The precise loudness of every gravitational wave chirp is therefore a cosmic probe, a way to test for these unseen dimensions. By meticulously comparing the observed strength of each signal with the strength expected based on its distance, scientists can search for any anomalous dimming. So far, the data from LIGO and Virgo have shown no such loss. The waves arrive with exactly the power we anticipate, ringing true across billions of light years. This silent consistency speaks volumes. It places incredibly stringent limits on the possible size and nature of any extra dimensions. Current observations have effectively ruled out the existence of large extra dimensions down to scales finer than a human hair. This might sound surprisingly large, but in the realm of theoretical physics, it is a monumental constraint. It immediately eliminates a wide swath of models that predicted gravity could bleed away into dimensions of that scale or larger. Each new black hole merger we detect tightens these limits further, cornering the possibilities for a final theory of quantum gravity. The universe is using its most violent events to tell us what it is not, quietly closing doors to entire landscapes of imagined physics, and guiding us toward a simpler, if perhaps more profound, truth. Some of the black holes we are hearing might be ancient fossils, relics from the very first second of the universe. These are not the corpses of dead stars. They are primordial black holes, hypothetical objects that could have formed in the seething, dense chaos of the Big Bang itself, from the raw energy of the newborn cosmos. Their existence has long been a tantalizing possibility, and now, for the first time, we have a real dataset to test the idea. The key lies in the masses of the black holes we are detecting through gravitational waves. Stellar mass black holes, the kind formed from collapsing stars, follow a certain expected pattern. Their masses are shaped by the complex physics of stellar life and death, which should produce a specific distribution, a predictable range of sizes. But what if we look at our growing catalog of mergers and see something strange? What if we find a population of black holes with masses that do not fit this stellar model at all? Some of the black holes we have already detected, especially the lighter ones or those in the mysterious gap, are perfect candidates for this investigation. If a significant number of these merging objects are primordial, it would mean our universe is seeded with invisible, ancient black holes from the very beginning. This idea leads to one of the most profound implications imaginable. Primordial black holes are a leading candidate for the universe's missing mass, for dark matter itself. For decades, we have known that most of the matter in the cosmos is invisible, detectable only by its gravitational pull on galaxies. We have searched for exotic particles, for WIMP and actions, with no direct success. But what if the dark matter is not a sea of tiny particles? What if it is a vast population of these primordial black holes, scattered throughout the cosmos? The gravitational wave observations are now placing critical constraints on this possibility. If all the dark matter were made of primordial black holes of a certain mass, say around 30 solar masses, we would have expected to see many more mergers than we actually have. The fact that we see the number we do suggests that primordial black holes can only make up a small fraction, perhaps less than 1%, of the total dark matter. Yet, the door is not completely closed. They could still be a component of it, hiding in a different mass range that our current detectors are less sensitive to. Every new chirp adds another data point to the census, another clue in the hunt for these primordial ghosts. Finding even one would be a discovery of monumental importance, a direct link to the universe's explosive birth, and a fundamental shift in our understanding of what exactly the cosmos is made of. Even gravity's own ripples are not immune to the warping of spacetime. Just as a massive galaxy can bend the light from a distant quasar, acting as a cosmic magnifying glass, so too can it lens a passing gravitational wave. The effect would be both strange and spectacular. A single chirp from a black hole merger, traveling for billions of years, could be split into multiple paths by the gravitational field of an intervening galaxy cluster. We would then detect not one, but two or more identical copies of the same cosmic crash, each arriving at a slightly different time. It would be a perfect echo, a replay of the same violent event days, weeks, or even months apart. These repeated signals would be fainter, like an image seen through a fractured lens, but their identical waveform would be the telltale sign. While we have not yet confirmed a lensed gravitational wave, the first tantalizing candidate events are already sparking intense debate. Finding one would be more than a curiosity. It would transform gravitational waves into a precision tool for cosmic cartography. Because the amount of lensing depends on the total mass in the foreground, including the invisible dark matter, a lensed wave would give us a direct measure of the mass of the entire lensing object. We could literally weigh a galaxy cluster by the way it bends a gravitational chirp. This would offer a new, clean way to map the distribution of dark matter in the universe, free from the assumptions that can complicate measurements using light alone. The echo of a single collision could illuminate the invisible scaffolding of the cosmos, revealing the hidden architecture that guides everything we see. The echoes of colliding neutron stars are reaching right into our laboratories, reshaping the very foundations of nuclear physics. For decades, scientists have relied on massive particle accelerators to slam atomic nuclei together, creating fleeting, incredibly hot states of matter to study the strong nuclear force, the glue that holds protons and neutrons together. But these terrestrial experiments have a fundamental limit. They cannot reach the staggering densities found inside a neutron star, where matter is crushed to a state so extreme it no longer resembles anything we know. A single sugar cube of this material would weigh more than 1 billion tons on Earth. This is the realm of the neutron star equation of state, the ultimate rulebook for matter under infinite pressure. And until recently, it was a complete theoretical mystery with dozens of competing models but no way to test them. Now, the subtle stretching of neutron stars just before they merge, their tidal deformability, gives us that test. When two neutron stars spiral together, their immense gravity stretches them into teardrop shapes. How much they stretch, how easily they deform, is a direct probe of their internal stiffness. Are they relatively soft and squishy, or incredibly hard and rigid? The gravitational wave signal from a merger carries the precise signature of this deformation. The data from the first observed neutron star collision immediately ruled out the most extreme models. It told us that neutron stars cannot be too stiff. They must have a certain amount of give, a squishiness that allows them to deform significantly under tidal forces. This single measurement eliminated a host of theories that predicted exotic forms of matter, like pure quark soup or hyperin condensates, that would have made the stars so rigid they would barely deform at all. Every new neutron star merger we detect adds another crucial data point. By measuring the deformability of neutron stars of different masses, we are slowly piecing together the entire equation of state. It is like trying to understand the properties of a mysterious, impossibly dense material by gently squeezing different-sized samples of it from a distance of 100 million light-years. This cosmic data is now guiding the physicists working in underground labs and at particle colliders. It tells them which theoretical paths are fruitful and which are dead ends, effectively using the universe itself as the ultimate high-energy physics experiment. We are no longer just astronomers. We are nuclear physicists, using the collisions of distant, dead stars to read the fundamental rules that govern the fabric of matter itself. The final dance of two black holes tells a story written in spin. Every gravitational wave signal we capture carries a hidden fingerprint, a precise record of how fast these cosmic giants were rotating before they merged. Just as a figure skater pulls in their arms to spin faster, a black hole's rotation is a fundamental property, a kind of cosmic momentum locked in from its birth or acquired through a violent life. Decoding this spin from the waveform is like learning to read a new language, one that reveals the entire life history of the system. We have found that some black holes are spinning at a staggering fraction of the maximum speed allowed by physics, a whirlwind of warped spacetime. Others, surprisingly, are barely rotating at all. This simple distinction, fast spin versus slow spin, acts as a powerful forensic tool, pointing directly to how these pairs came to be. Imagine two black holes that were born together as massive twin stars. As they evolved, they could have transferred mass and angular momentum back and forth, spinning each other up like a cosmic merry-go-round. This process would leave both black holes with spins that are aligned with their orbital motion, a clean, orderly signature of a shared life from beginning to end. This is the isolated binary evolution story. Now consider a different origin within the crowded core of a globular cluster. Here, black holes find each other through gravitational encounters. They are not born partners. They are strangers thrown together in a chaotic dance. In this environment, their spins will be randomly oriented, tilted, and misaligned with their orbit. There is no gentle transfer of mass, no long-term relationship to align them. The data is now speaking clearly, and it tells us that both of these stories are true. We have detected binary black holes with spins that are neatly aligned, the products of a quiet, isolated stellar life. And we have also found systems with wildly misaligned, or even negligible spins, the clear calling card of a dynamic encounter in a dense stellar city. Each merger is therefore more than just a crash. It is a historical document. A rapidly spinning, aligned pair tells a tale of two stars that lived and died together. A slow spinning or tilted pair whispers of a violent past in a crowded stellar neighborhood, a partnership forged by chance and gravity. By listening to the spin, we are reading the autobiography of the darkness itself. A single, faint chirp in a detector is just data. The real discovery is how that ripple becomes a global alarm bell. This entire system of rapid alerts is a technological marvel in its own right, a logistical ballet that unfolds in mere minutes. The process begins the moment a suspicious wobble appears in the data streams of LIGO and Virgo. Sophisticated software algorithms, running in real time, are constantly on the hunt for patterns that match the signature of a cosmic collision. When they find a candidate, the system does not wait for human approval. It automatically springs into action. The first and most critical step is localization. By comparing the precise arrival time of the wave at each of the widely separated detectors, the system can triangulate the source's position on the sky. It is like hearing a sound with several microphones and using the tiny differences in when the sound arrives to pinpoint its origin. This creates a probability map, a large, fuzzy patch of sky where the event most likely occurred. Within minutes, an automated alert is packaged with this sky map and blasted out to a network of over 100 observatories around the world and in space. This is not a casual email. It is a high-priority digital shout, a call to arms for the entire astronomical community. The message contains everything a telescope needs to know: the estimated distance, the type of objects that likely collided, and most importantly, where to point. Imagine a fire alarm that not only sounds, but also tells every fire station in the world the exact neighborhood where the fire is burning. This is the scale of coordination we are talking about. From a quiet data stream to a global observing campaign in under 10 minutes, this rapid response system has fundamentally changed the pace of discovery. It turns a solitary whisper in spacetime into a chorus of focused inquiry, proving that when the universe speaks, the entire world is now ready to listen as one. This relentless cosmic squeezing is revealing the true nature of matter itself. The tidal deformability we measure from neutron star collisions is a direct window into the equation of state, the ultimate rulebook for matter under the most extreme pressures imaginable. Think of it like testing a mysterious, impossibly dense material by squeezing it from 100 million light-years away. The equation of state is simply the relationship between the pressure inside the star and its incredible density, and it dictates everything about the star's fundamental properties. Before gravitational waves, this equation was a theoretical playground with dozens of competing models, but no way to know which one was correct. Now, the data from these collisions is acting as a ruthless referee. The amount a neutron star stretches tells us if the nuclear matter inside is stiff and rigid, or soft and squishy. A very stiff equation of state would mean the star is highly resistant to deformation. It would be like trying to stretch a diamond. Such a star could support a very large maximum mass and would have a relatively large physical radius. A soft equation of state, on the other hand, means the matter is more compressible, like a dense foam. The star would be more deformable, have a smaller maximum mass, and a more compact size. The gravitational wave signals we have observed so far are pointing toward a universe where neutron star matter has a certain amount of give. It is not the most rigid possibility. This single finding has already ruled out a host of theoretical models that predicted the interior would be filled with exotic forms of matter like pure quark soup or hyperons, which would have created an incredibly stiff star that barely deforms at all. By narrowing down the equation of state, we are also zeroing in on the possible sizes of these cosmic atoms. We now know that a typical neutron star with a mass 1.4 times that of our Sun likely has a radius of around 11 to 12 kilometers. That is an entire city's worth of ultra-dense matter compressed into a sphere smaller than a major metropolis. This precise measurement is also telling us the absolute maximum mass a neutron star can possibly have before it collapses into a black hole. Current data suggests this limit is close to 2.3 solar masses. Any heavier, and even the powerful nuclear forces cannot withstand the pull of gravity. Every new neutron star merger we detect adds another crucial data point, another squeeze of the cosmic material that further refines this equation. We are slowly, ripple by ripple, reading the fundamental instructions for how matter behaves when it is pushed to its absolute limit. Einstein's theory holds one last, subtle secret about these cosmic crashes. Even after the final ring-down fades and the merged black hole becomes silent, its legacy remains written into the fabric of the cosmos. The violent event should leave behind a permanent scar on spacetime itself, a phenomenon known as gravitational wave memory. Picture the wake of a ship cutting through a calm sea. Long after the vessel has passed, the water is left permanently displaced, its level subtly and forever changed. A black hole merger does the same to spacetime. The passing gravitational waves are so powerful that they do not just temporarily stretch and squeeze space. They leave it permanently deformed. This is not a temporary ripple. It is a lasting step, a change in the distance between any 2 points in the universe that persists for all time. This incredible prediction arises directly from the nonlinear heart of general relativity, where gravity itself creates more gravity. The energy carried by the initial waves generates its own gravitational field, which in turn creates this final, permanent offset. It is a signature of the theory's deepest self-interaction, a ghostly fingerprint proving that spacetime is a dynamic, malleable substance that can be irreversibly altered. Yet, for all its theoretical elegance, we have not yet caught this ghost. the effect is incredibly faint, a change in distance thousands of times smaller than the width of a proton over a span of 4 kilometers. Detecting it requires observing not just the loud chirp of the merger, but the enduring silence that follows, searching for that infinitesimal, permanent shift. Our current detectors, LIGO and Virgo, are not quite sensitive enough to pick out this single, quiet note from the constant background noise of the Earth. The hunt for memory is therefore pushing data analysis to its absolute limits. Scientists are trying to combine the signals from multiple mergers, stacking them together like layers in a composite image, hoping the combined effect will rise above the random noise. Finding it would be a monumental achievement. It would be a direct observation of gravity's ability to write its history directly onto the universe. A final, elegant confirmation of a century-old idea in its most extreme environment. Its continued absence, however, is just as compelling. It reminds us that even our most advanced instruments are still straining to hear the universe's quietest whispers, and that the deepest secrets of spacetime are still waiting to be revealed. This global network of ears is what makes modern gravitational wave astronomy possible. It is not just the 2 LIGO detectors in the United States listening alone. The critical partners are the Virgo detector in the Italian countryside and the newly operational Kagra Observatory in Japan. Each new instrument added to the network transforms our hearing from a simple sense into a sophisticated form of cosmic triangulation. The principle is beautifully straightforward. A gravitational wave, moving at the speed of light, will reach each detector at a slightly different time. By measuring these minuscule delays, sometimes as small as a few millionths of a second, scientists can work backwards to calculate the direction the wave came from. It is like hearing a clap of thunder with several microphones spread across a city. The tiny differences in when the sound arrives at each microphone tell you exactly where the lightning struck. With only 2 LIGO detectors, the sky location for a gravitational wave source was incredibly vague, often a sprawling patch of sky covering hundreds of square degrees. That search area could contain millions of stars and galaxies, making the hunt for a flash of light like finding a single specific grain of sand on a vast, dark beach. The addition of Virgo changed everything. A 3rd detector creates a powerful triangle of measurement. Suddenly, that huge, fuzzy patch of sky shrinks dramatically, often down to just a few dozen square degrees. This is a revolution in efficiency. Instead of asking telescopes to scan an impossible swath of the cosmos, we can now give them a much smaller, more precise cosmic address to investigate. This precise localization is the engine of multi-messenger astronomy. It is the difference between a vague rumor of an event and a specific tip about where to look. When a signal arrives and the network quickly calculates its origin, that automated alert sent to observatories around the world contains a far more useful map. Telescopes no longer waste precious time scanning empty space. They can point directly at the most likely galaxies within that smaller region and start collecting data almost immediately. This is how we caught the light from that neutron star merger in 2017. Without Virgo's data, the search area would have been too large, and the fading glow of the kilonova might have been missed entirely. Now, with Kagra coming online, this global network grows even stronger. A 4th detector, especially one located in Japan, further refines our triangulation and provides a crucial check against false signals. The more ears we have listening to the cosmos, the more clearly we can hear, and the more quickly we can turn to see what is making the sound. Our cosmic listening posts are tuned for more than just violent crashes. They are also searching for a far more subtle and persistent sound, a constant, pure tone humming from the heart of a spinning neutron star. This would be the signature of a continuous gravitational wave. Unlike the brief, rising chirp of a merger, this signal would be a steady, monochromatic drone, lasting for years or even centuries. It would be generated by a tiny asymmetry on the neutron star's surface, a cosmic mountain just a few centimeters high. Even this minuscule imperfection, spinning hundreds of times every second, would make the star wobble slightly, rhythmically shaking the fabric of spacetime itself. It would be like a perfectly tuned bell, ringing forever in the silent void. Yet, despite years of searching through the data, our detectors have heard nothing. This profound silence is not a failure. It is a powerful discovery in its own right. The absence of these continuous waves tells us something fundamental about the nature of neutron stars. It places a strict upper limit on the size of these mountains. We now know that the crust of a neutron star must be almost impossibly strong and perfectly smooth. Any deformations must be smaller than a few centimeters across an object that is over 10 kilometers wide. To put that in perspective, that is smoother than a billiard ball scaled up to the size of the Earth. This incredible rigidity informs our models of the star's internal structure. The crushing gravity of a neutron star is so immense that it should flatten any ordinary mountain into a featureless plain in an instant. The fact that we do not detect these waves means that the crust is not just being passively flattened. It is actively supporting itself against this unimaginable pressure, a testament to the strength of nuclear forces operating at densities we cannot replicate on Earth. This non-detection is steadily ruling out theories that suggested neutron stars could have larger, more permanent deformities. It tells us that these cosmic cinders are not just dense. They are among the most perfect spheres in the entire universe. Their flawless silence speaking volumes about the extreme physics that govern their existence. The silent collisions of black holes are becoming our newest cosmic lighthouses. We have already seen how a single neutron star merger offered a fresh measurement of the Hubble Constant. But that was merely the first note in a much grander symphony. The true power of this new tool, what scientists call a standard siren, is only now being realized as we look to the deep universe. Black hole mergers are the key. Unlike the fleeting light of a supernova, which can be obscured by dust or confused with other stars, the gravitational wave chirp from two colliding black holes is pristine. Its waveform directly encodes the system's intrinsic loudness, giving us a direct, absolute measure of its distance without any intermediate steps. This is a clean cosmic ruler, unfettered by the assumptions that can creep into the traditional cosmic distance ladder. As our detectors become more sensitive, we are beginning to hear these events from much farther away, from redshifts that correspond to billions of years in the past. Each new detection at a different cosmic epoch adds a data point to our map of universal expansion. Imagine being able to plot the universe's growth rate not just in the recent past, but across its entire history, using nothing but the echoes of dark collisions. This is the ultimate promise of gravitational wave cosmology. By compiling a catalog of standard sirens at various distances, we can trace how the expansion rate has changed over time, probing the nature of dark energy itself. Does the push of dark energy remain constant, or has it varied over the life of the cosmos? The answer is written into the changing distances to these merging black holes, a story told by the stretching of spacetime itself. We are on the verge of building a completely independent history of the universe, one written not in light, but in the quiet ripples of gravity. What hidden chapters of cosmic evolution will these dark messengers reveal when they finally speak from the dawn of time? But our current detectors are only listening to one part of the cosmic symphony. The LIGO and Virgo observatories are tuned to hear the high-frequency chirps and thuds from stellar mass collisions, the violent, rapid-fire events that last for mere seconds. A far grander, slower music fills the cosmos, and we are finally building the instruments to hear it. This is the opening of the low-frequency gravitational wave window, a realm of space-time ripples with cycles that last for hours, years, or even decades. To catch these vast, rolling waves, we cannot rely on Earth-bound laboratories. The arms of our ground-based detectors are simply too short. We must build an observatory in the quiet, stable environment of space. This is the promise of the Laser Interferometer Space Antenna, or LISA. Imagine a triangle of three identical spacecraft, trailing behind Earth in its orbit around the Sun. They will fly millions of kilometers apart, connected only by laser beams. This gigantic instrument will be sensitive to gravitational waves at frequencies far below what any ground-based machine can ever detect. What will it listen for? The stately billion-year dance of supermassive black holes. When two galaxies collide, the colossal black holes at their cores eventually sink to the center of the new merged galaxy and begin their own slow spiral. Their orbital waltz, lasting millions of years, produces a constant low-frequency hum of gravitational waves. LISA will hear this. It will allow us to watch, in real time, as galaxies merge across the universe, tracing the growth of the most massive structures in the cosmos from their gravitational soundtrack alone. Beyond these giants, LISA's sensitive ears will also pick up the chorus of millions of binary white dwarf stars within our own galaxy. These dense stellar embers orbit each other rapidly, and their combined whispers will create a steady background rumble, a gravitational map of the Milky Way's stellar graveyard. This low-frequency window will reveal a completely different side of the universe, one operating on scales of time and space we have never before been able to access. We will probe the entire history of cosmic structure formation, from the first seeds of galaxies to the mighty giants we see today, all by listening to the slow, deep vibrations they imprint on spacetime. The age of low-frequency gravitational wave astronomy is dawning, promising to unveil the universe's most patient and powerful rhythms. We have surfed the ripples of spacetime through 30 groundbreaking discoveries, a journey that began with a single whisper from colliding black holes and unfolded into a multi-messenger symphony of light and sound. This new sense has fundamentally altered our cosmic perspective, confirming Einstein's century-old dream while simultaneously revealing a universe far more violent, dynamic, and inventive than we ever imagined. From the first chirp that opened our ears to the cosmic collisions, forging the very gold in our jewelry, gravitational wave astronomy has proven to be one of the most transformative tools in the entire history of science. The universe is no longer a silent movie. It is a vibrant, roaring epic, and we have finally learned how to listen to its soundtrack. This is not the end of the story, but a spectacular beginning. The next decade, with more sensitive detectors on Earth and new observatories in space, promises a tidal wave of revelations. We will hear the birth cries of black holes from the earliest stars, map the invisible dark matter with lensed echoes, and perhaps even catch the primordial hum of the Big Bang itself. What do you think will be the next big discovery? Let us know in the comments below. And don't forget to subscribe so you don't miss our next deep dive into the cosmos.